talked about what you're seeing down here at the bottom of the page. This is a time domain sinusoidal, periodic sinusoidal representation of two AC signals, a voltage and a current. And it's a system where the current is actually lagging the voltage. So it's what we call a lagging power factor. Once we discuss power factor, you'll understand a little more what that is. But there's a power factor angle, which is this angular difference right here between the voltage and the current. And what I'm showing here is what we call a periodic scalar function, and so I'm highlighting those. These are the mathematical expressions for those two signals, and I'm going to call them V alpha and I alpha. And when we talk about leading and lagging power factor angles, it's really confusing to try to understand, looking at this waveform, whether it's leading or lagging. I get screwed up every single time. And you say, okay, I told you it's a lagging power factor. What does that mean? It means that the angle, the power factor angle, is less than zero. It's a negative angle. And so if you look at this mathematically, what that means is that, first of all, the voltage that we're giving you, V alpha, is referenced at zero angle. It doesn't have, it's kind of our reference, point of reference. It's a cosine. And so if you say this point right here at the bottom, that's t equals 0. At t equals 0, the cosine, you would be saying omega e times t is 0, so cosine of 0 is 1, and so you would be at a scalar value of square root of 2 times V RMS, and we're giving it this way and showing it in terms of RMS quantities, because that's really what you can measure in, say, a lab environment, is the RMS voltage or the RMS current. Another way to look at this here is that these two things here are that's a peak voltage, and this is a peak current. So the current, though, is displaced from the voltage by this angle. This x-axis that we are referring to here is not a time axis, it's omega e times time. That's the same thing as saying an electrical angle, theta e. And so you could make your equations look a little simpler here and just say cosine of theta e, and this could be cosine of theta e plus phi power factor. And it's the reason we did this is because it's a periodic waveform, and it's easier to think of things in terms of angle as opposed to time. And so the repetitive part of this happens every 2 pi radians. So that's really what we're looking at. We're looking at 2 pi period between the peaks of these two, the voltage or the current. So we could think of the progressing along this axis, the theta e axis, when theta e equals phi pf, then we would be hitting, actually I think I have this off a little bit. that's when we would hit the peak of the current. And so this tells us that this has to be a negative angle for that to work. Now this is really, we have to go through a lot of math and a lot of mathematical gyrations to get our head around this, looking at it, say, on an oscilloscope. So there's a much better way to look at things, and that is to look at the same scalar signals in a polar reference frame. So there's an easier way, is let's look at this in a polar reference frame. And what is a polar reference frame? Well, if you'll recall, and you probably learned this in, I'm assuming, in your 361 class, because electromagnetics are often looked at in one of the three different reference frames, the XYZ, or the cylindrical reference frame, or the XYZ is called Cartesian coordinates, or the spherical reference frame. So the polar really kind of correlates with a cylindrical reference frame. And you can think of right along this blue vector, which is representing V alpha, actually, that would be considered the R plane of a cylindrical reference frame. And then you have another plane, which is an angular plane, which is I'm going to call theta. And of course, in the cylindrical reference frame, I'm showing this little dot at the center. That would be you could have it coming out here, right? That would be Z. So this is correlating this with geometrical reference frames that you use for electromagnetics. But now we also, if you just take the two planes, the R and the theta, you have a polar reference frame, a two-dimensional polar reference frame. And so it's very convenient to use what's called phasors. And so what is a phasor? A phasor is really a combination of two words, phase plus vector. So it's a phase vector. And if we can actually represent these scalar functions as phasors. And so the blue line is the voltage that I just kind of highlighted there, and it's right now lined up. I'm going to erase these cylindrical coordinates now, clean this up just a little bit. I've taken two Cartesian axes that are 90 degrees out of phase with each other and put them on this, superimpose them on top of the polar coordinate frame. And what these are the alpha axis. So there's an axis where everything to the right of the center point is a positive alpha, and to the left is a negative alpha. And a beta reference frame, everything to above this origin on the y-axis is plus beta, and everything below is negative beta. So I've superimposed those two axes on top of this. And what we're doing is we're saying I have a phasor that's going to be rotating at an angular velocity of omega e. Okay, so both of these vectors, the blue one, which represents the voltage, and the green one, which represents the current, they're going to stay fixed in their relationship to each other by this angle phi pf, the power factor angle, but they're both going to be moving at a rate of omega e. But omega e is 2 times pi times an electrical frequency, where the frequency is equal to 1 over the period over which the periodic waveform repeats itself. So you can imagine that these two phasors are moving at a constant rate, and I'm going to show you. So for example, I've just moved them and frozen them in time at a different position, and this position is theta e. That is a position in time, and it actually will represent a scalar voltage and a scalar current point at that point in time. To illustrate this point, if you look at the position we're at right now with these two phasors, we're at the position of theta e equals 0. And so the theta e, this is just by convention, is moving in the counterclockwise dimension, very similar to what you would see the direction you'd be going in the cylindrical reference frame or the polar coordinate frame. So at theta e equals 0, we're at these 2 points shown down here, looking at the time domain, the blue and the green. And that those 2 points are the scalar values for V alpha and I alpha. These same points are represented on the alpha axis. And so this point right here is that point on the alpha axis. The green dot, if you were to reflect the green phasor for current onto the alpha axis, so essentially that's a cosine of phi pf at that point in time, you're going to find out where you are on this y-axis below. So I'm showing those same 2 points on reflected onto the alpha axis, and notice that we're just ignoring the beta axis. It's not really doing anything for us right now. Now, if you look at things in the phasor representation, it's easy to understand lagging versus leading. I'll show you why. So these two phasors are moving, and which phasor hits the alpha axis first? It's the blue phasor. So the voltage is leading the current. The current is lagging the voltage. The current is going to hit the alpha axis after the voltage hits it. They're both going in this direction. If I had a leading power factor, then the green vector for current would be in this quadrant up here. And so, imagining that these two things are rotating, the green phasor would have hit the alpha axis first, so the current would have been leading the voltage. It's way easier to understand leading and lagging looking at it in this scalar than trying to figure it out the way we tried to do it mathematically, looking at it with these waveforms down here. So to illustrate, I'm showing us at an instantaneous point of 42 degrees. And so the voltage is moved into this quadrant up here, and the current is following it at a fixed angular displacement of the power factor angle. And the scalar values are where we're at. So you could reflect the green phasor onto the alpha axis, and this green dot on the alpha axis is the same as the green dot that gets reflected onto this amplitude axis for the current, and the blue dot reflects onto the alpha axis at that point. And so you've got this phasor that's moving and it's rotating. So here it is at 90 degrees. So at alpha E equals 90 degrees, if you reflect the phasor amplitude of the voltage, the blue phasor, onto the alpha, it's 0. Oops, you've moved to the center right there at 0, and then so on. You can go negative here. So now we're down here, we move to another angle, so the scalar amplitude of the voltage is a negative. So when I'm at 180 degrees, I'm on, let me show that one, I'm about 180 degrees. I'm at a negative peak amplitude. That's the same point as this point here of the voltage. That's the 180 degrees point. Okay, so are there any questions about this? Does this make sense to you? Looks like you guys are thoroughly...
For the most part.
Yep, makes sense for the most part. So this is going to be very helpful when we start to talk about three-phase, and that's kind of why I'm belaboring it now. But there's another point. We're going to basically segue into what we call phasor representations of AC circuits from here, and I want to show you how we get there. But before we do that, let's look at something else. What are we doing with this beta axis? Why did I use that? Well, if I were to take, let's go back here. So notice with this function on the bottom, I'm running with an axis right there. This is the t equals 0 point. If I were to move that y-axis back to this point right here, I've got a sine, don't I? It's not a cosine, it's a sine wave now. And so it's really arbitrary whether you say V alpha or I alpha are sine or cosine. See, it's an arbitrary choice. It depends on where you pick that t equals 0 reference point. Think of like a scope, like where you're going to trigger. You're going to try to trigger at a peak or a zero crossing. Easier to trigger at a peak, so you can it's easier to reference things like cosines when it comes to sine waves if you're using an oscilloscope. So when it comes to this phasor representation of things, if we're assigned, we're going to use the beta axis. And these 2 points that I'm showing here, the voltage point is now reflected on the beta. That's the same as this point right here. And the current reflects onto the beta. That's the same as that point right there. And you can think, but again, these things are moving at a constant rate of omega e, and you could think of crossing the beta axis. The voltage is going to hit the beta axis first, followed by the current. So this is a lagging power factor angle. And we can also see that if we assume that the theta direction, or the theta e direction that we're moving, is in the counterclockwise direction, then I'm showing this phi pf like this. It's a negative number, it's a negative angle, so it's a lagging power factor. Okay, and now
So would this I'm sorry not to interrupt you.
no, yeah,
Would
please
this
do.
with because this is it because this is lagging, this would be like a circuit that would have like a heavy inductive load. Am I right about that? And then if it was
Yep,
leading, it would be a heavy capacitive load.
that's correct, that's absolutely
Okay.
correct. Yep.
All right. Cool.
So
Cool.
we're going to actually show you all of that um, shortly. So anyways, if you want to say, well, what is mathematically, what are we talking about here? We have this scalar representation, v peak cosine, and I'm just going to use theta e to start with, and I've shown you writing it in terms of the quantities that we're typically going to be working with. And as I point out in the previous lecture, we're always operating at a steady state in this class. We don't talk about dynamics. So we're at an RMS constant value of voltage, and this frequency is moving at a constant rate of omega e. Now in the scalar, this is actually a voltage that's varying with t, and I was calling it V alpha because it's a cosine and we're using that alpha axis. And if I want to write a function for the scalar, what would that be? It would have to be giving us the same value of V alpha of t, and that would be the real component of square root of 2 V RMS E J omega E t. If you're familiar with Euler's expression, E J theta is equal to the cosine of theta plus J sine of theta. So if I were to plug that into here, what would I get? So I know that omega E t equals theta E, so that would be cosine of theta E plus J sine of theta E. So the real part of it is just that. So basically what I'm showing you here is a proof of where this expression for the phasor, which is this expression right here, comes from. If we want to consider the current, we have an angle offset there. And the phasor representation for that is the real component of square root of 2 I RMS e to the j omega e t plus phi pf. And so we could, in a similar fashion, I could show and prove to you that these two are equal to each other using the Euler expression. Now what we have, a common thing with the phasor, is the V alpha t square root of 2 V RMS E J omega E t, and then I can just be general and say a phase angle, a general phase angle, and it's 0 degrees because we're referencing everything to where the voltage is. And then the I alpha of t would be square root of 2 VRMS EJ omega E t plus phi power factor. Now if I factor out the temporal varying things here, so with phasors, if you're operating at the same frequency, which you will if you're using a sine wave and it's a pure sine wave, then you could rewrite these two equations like this. And what I'm representing this is a phasor that's temporally fixed in time. It's got this little hat over it here, times EJ omega ET. And what is that?
Can I ask a quick question?
Sure.
Why are you able to remove that time factor from the VRMS? Like, how are you able, like, I understand your equation, I guess, but I guess, like, what allows you to get rid of that time factor from the VRMS as just a quantity?
Well, we're not getting rid of it. It's always there, but we don't need it to solve the problem at a single frequency. And so
So
yeah,
you're saying, like, because that RMS is always going to be, like, because we've talked about in the past, like in the last lecture, you said that if we're looking at the RMS value over over a waveform that's continuous, it's basically going to be pretty consistent because of how the RMS value is taken, because it's over one period.
that's
So
right.
therefore, we can kind of assume that moving forward, that even though that time factor is important, because if you want to look at a specific location, it doesn't necessarily affect the whole of the system, because the magnitude is going to remain basically unchanged for the RMS value.
Exactly. That's
Okay. All
exactly
right.
right.
That makes sense. Thank you.
And it's, as you can see, when we go and we look at scalar things, try to get back to this picture here, it's not really helpful to look at individual scalar points on this waveform, is it?
No, it's not.
Yeah, so what we need to
No,
do
it's not at
is,
all.
yeah, we want to come up with a way of looking at it that's helpful for us to know what's going on.
That makes sense.
So
That makes
then,
sense.
so what we are able to do is we're able to pull out this phasor representation of the voltage, VRMS EJ theta, and this is really the convention that we have decided to work with. So EJ theta, another way to write this is VRMS at an angle 0 degrees. And since EJ, your e to the j 0 degrees, that's the same as 1, right? So because we're referenced at 0 degrees, it's just one value, VRMS. The current, on the other hand, is going to look like this. So there's the current phasor, EJ omega ET. So if we ever want to go back to the time domain, we just put it back into this form. But we're going to pull this out and work with it. And this is I alpha. Now this is going to be I RMS e to the j phi power factor, or I RMS phi power factor. Another way to write this in a Cartesian coordinate reference frame would be I RMS cosine phi pf plus j I RMS sine phi pf, using Euler's expression. So we know that we have a real and we have a imaginary component for the phasor. So that leads us to this type of a representation of the two phasors that we were talking about. So there's the voltage phasor. This is the V phasor. VRMS 0 degrees, and the I phasor down here, V power factor for a lagging load. And this is what we're going to be working with. And this is where you need to get very practiced at solving these problems using phasor representations. So is everybody with me on this?
Yeah, that makes sense.
Yep.
Could we go back to that last slide where you're writing down the I alpha representation and cosine and sine?
Yeah, right here?
Yeah, thank you.
Yeah, sure. So does that make sense? Do you have a question specifically about that, or just want to see it?
Sorry, I just had to finish writing it down. I'm all good. Thank you.
Okay. Yeah, so this basically means that you're going to have a real component and a reactive component. The real component's going to be the RMS value times the cosine of the angle. The imaginary is the RMS times the sine. So what I want to show you now is this single phase circuit, an actual AC circuit. This is really what you're going to be seeing in your first lab. From lab 1, what you have in the lab is you have a variable source. Okay, so that's your variable source. So you can imagine this is something that you can go in and increase the amplitude or reduce the amplitude of the voltage, and you'll be able to measure the RMS voltage that you're producing what at the load side. And so there internally there's a power meter that's in this box right here, and what you have on the other end is a load, and the load is an impedance that has, in phasor form, it would have a impedance magnitude and an impedance phase. And the actual implementation of your power meter is really implementing all the stuff that we talked about so far, because what it's doing is it has a voltage sensor here that has a nearly infinite impedance, measuring the voltage from line 1 L1 to this endpoint, and it's going to be processing that signal and calculating an RMS, and it also has to sense the zero crossings of the voltage and compare them to a signal that's measured through a current sensor with a nearly 0 ohm impedance, and then it's going to calculate the power factor angular difference between the voltage and the current and the RMS current. And so you're really going to see in your meters readings voltage, current, and power factor angle. And the power factor angle, there's a little bit of nuance with the lab equipment. It's because we're trying to fix this, but actually I think we're going to all Lucas Knoll equipment anyway now, and that's the German equipment. So I guess the Germans like to put a negative sign in front of leading power factors for some reason. And so you have a little sign difference as to what you're going to measure on that meter compared to what I've told you in the class. But if you look at the feedback equipment, which is the other set of equipment in the lab, there's really two sets of equipment. Depending on what station you're at, then the power factor angle will follow the sign convention that I've talked about here. That's just something that you'll just have to compensate for. But really, at the end of the day, what we have is we can represent what you are measuring in the lab as a phasor circuit. And what does that phasor circuit look like? Well, you may have, for example, the Z is your load. And what you'll be able to do in the lab is connect resistors, inductors, and capacitors in series, parallel, and various configurations. Looking into this, there is an impedance of the load, Z load. And so I'm going to skip over one point here, and maybe when I record the lecture I can add it in. But what I'm showing is you've got an R and you've got an L here. In the phasor representation, what is this going to look like? It's going to be an R. I'm going to maybe give you something to bridge this gap in the lecture, but this is something you all should know this already. The inductive load is a reactive load with a reactance XL. And let me see if did I talk about that in the next slide anyway. I don't. I assume you already know this. So XL is what? The voltage across the L. And if we were going to show this voltage as a scalar, it would be the L value times the derivative of the current that's going through that L. But in phasor form, we can write it this way. It's the same as saying J, which is an imaginary term, times the frequency omega E times the L. That's JXL. So that's what this circuit looks like in phasor form. So I'm going to cross this little. So let's look at how we can use phasor analysis to solve problems with an AC circuit. What we have here is a single phase circuit with a parallel resistive and inductive load, representing the inductive load with a reactance of XL, which we know, again, as we said, is XL is omega E L. And we see that we are applying a voltage V hat here in phasor form, VRMS, referenced at an angle 0. And that's our source. That corresponds to this phasor here, all on the real axis. Because of this load, we are drawing a current, shown here. And since it's inductive, it has a lagging power factor. This current feeds into two branches, and so we could solve and find the current by considering or solving KCL at this node. So the total current going into the node would be the sum of the current going into this reactive branch, the imaginary part of the phasor current I, and the current going into the real branch, the real component of the I phasor. What are those currents in the two branches? The resistive branch, the real part of the total current, is going to be the applied voltage across that branch, which is simply VRMS. If it has again the 0 degree phase angle, but since it's a 0 degree, it's all in the real axis, so we can just ignore that, divided by the resistance R. So it's VRMS over R. The imaginary part of that current is VRMS over JXL. Since the J is on the bottom, we want to move it to the top so that we can show it in the Cartesian representation of the phasor with this J right here. So then that makes it negative, which makes sense because it's lagging current and we have a negative angle right here. So it's negative J V RMS over XL. Therefore, the total current going into this load is VRMS over R minus J VRMS over XL. So let's analyze what's going on here. We know that we're going to use a phasor diagram to do this analysis. Phasor diagrams are something that we will use in this class that will be very helpful to us in checking the math of our phasor math when we solve a difficult problem. And this is a really simple problem, by the way, because of the fact that we're just simply solving KCL at this node, and if we're dividing up between purely reactive current and purely real current. This is not the typical circuit. The circuits we will be working with will be more complicated than this. What I'm saying again is that I have a real and imaginary axis. I have one quantity on the real axis, IR, and I have another quantity on the imaginary axis, which was negative II. So these are both phasors. What I can do, I can take this phasor right here and I can move it there. So this phasor is exactly, it's negative JII. This is how what I just did is I'm summing these two together. So I'm saying IR minus JII is going to be equal to some phasor I. And then to find what this is, I would start at the origin and draw a phasor line to the point where I ended. And that is the phasor current. So this is really an example of phasor math using a phasor diagram. It's a very simple example, but this principle can be applied quite easily. So looking again at a phasor diagram, the voltage on the real axis, the current for a lagging load is down here. I can take this current and reflect it onto the real axis, and the current that I would get on the real axis, I can represent it as a phasor as well, is IR, and that is, it would be IRMS times the cosine of the power factor angle. I could reflect this phasor onto the y imaginary axis, and the current that I would get here, putting the phasor on that axis, would be II equal to I RMS sine of the power factor angle. We had this example of purely paralleled R and L. So we had an R branch, an L branch. This is XL. The impedance would be shown as JXL. And to be exact with what I'm showing, because I'm showing this as a phasor, I should put a J here and a J right there. The sum of these two currents is the total current I coming in. And I would also know that because for this specific circuit, let's say I don't know what R is and I don't know what XL is, I could solve for them by saying, for example, I RMS cosine phi PF equals V RMS over R. That's the real part of the current. And I could solve for XL by saying that I RMS sine phi PF. And now I'm just going to say this is a magnitude. I'm not going to worry about what the sine of that angle is. It's equal to V RMS over XL. Another observation is because it's lagging, phi PF is less than 0. So that would mean that I would be plugging a negative number in here. But since if you take a cosine of a positive or a negative, it's going to be a positive. But if you take the sine of a negative number, it's going to be negative. So mathematically, I'm going to get the right sign with the negative angle. Okay, let's consider a capacitive load. This is actually a leading power factor load. Now, if we have a capacitor, what is the reactance associated with this capacitor here? Well, the reactance is going to be XC equals, this is the magnitude of that, 1 over omega E times C. This comes from the fact that the voltage across a capacitor is equal to 1 over C integral of the current through that capacitor. So we can, in a like manner that we showed with the inductive load, convert this to a phasor form, taking the derivative of both sides. The current expressed in terms of the voltage would be equal to C dV dt. Which is the same as saying J omega C times the applied voltage across that if it were a phasor voltage. So this is the phasor representation of the current through that capacitor. And cleaning things up here, the real component of the current is the same as it was for the parallel inductive circuit, V RMS over R, but the reactive component of the current is J VRMS over XC, where XC equals 1 over omega EC. So for the leading power factor case, if we want to look at the phasor diagram, the current phasor is in this quadrant because we have a positive J. This is J VRMS over XC. The power factor angle here is greater than 0. It's a positive value. There's a phasor on the real axis for the real part of the current, which is VRMS over R. So the total current, I, is VRMS over R plus JVRMS over XC.